All right, welcome back. We are talking about magnetic torque and magnetic moment. I've got a wonderful example here for you. We've got a rectangular coil of area 10 square centimeters, carrying current of 50 amps, lying in a plane given by 2x plus 6y minus 3z equals 7. So this plane is not the z equals 0 plane, it's not the y equals 0 plane, nor the x equals 0 plane, such that the magnetic moment of the coil is directed away from the origin. Calculate its magnetic moment. All right, so um, previously we have shown, or we kind of derived, that the magnetic moment of a coil is I, which is the current the coil is carrying, times S, which is the surface area, times not surface area, but S is the area of the loop, the coil, and then times a unit vector that points in a direction normal to the loop. Okay, so we have all of these things except for AN, right? We've got the current 50 amps, and we've got the area of the rectangular coil, which is 10 square centimeters. So we just have to get a unit vector normal to this thing. So imagine a plane. Right, you have to use your imagination here. Here's the plane given by this equation, and lying in that plane is our rectangular coil, maybe like this. So we have to, and this can be hard to draw, but we have to get like that vector that's perpendicular to that plane. So how do we do that? Well, this goes back to calculus and dot products also. If you want something that's if you want the angle, if you want a normal vector, you can rely on the dot product. So our plane is given by this thing, and if we subtract the 7, minus 7, then we have this. Okay, now I'm going to use the dot product here. I'm going to show you that we can arrange this like a vector like this, x, y, z, 1, dotted with 2, 6, negative 3, negative 7 equals 0, right? So you agree with me there. So if you do the dot product of those two vectors, you get 2 times x plus 6 times y plus minus 3 times z plus minus 7 times 1 and equals 0, and that's the equation of our plane. Now, if the dot product of two vectors, so you can think of this as kind of a variable vector, and this is definitely a determined vector there. If the dot product of two vectors is 0, then they are orthogonal to one another, as we've talked about. So you can look at this here as being a vector that is orthogonal to this plane. And why did I not circle the negative 7? Because negative 7 just moves the plane around. It shifts it up and down parallel. Think about in one dimension, if you had x squared, what that function would look like, and then if you added 7 to it, all it does is shift it up, right? It's still, anything perpendicular to it is still perpendicular to it. So we don't have to worry about the constant there, but this thing that I've circled is actually a vector that would be perpendicular to our plane. It's not a unit vector, but it is perpendicular. So how do we get a unit vector in that direction? Well, we would take 2ax plus 6ay minus 3az, and then what do we have to do with that vector? Divide it by its length, right? So its length would be the square root of 2 squared plus 6 squared plus minus 3 squared. So that's 9, 36, 4, I think that's 49, so the square root of that is 7. And so our unit vector is 2/7 in the x direction plus 6/7 in the y direction plus, or minus, I guess, minus 3/7 in the z direction, like that. So that's our unit vector. So that's most of the work in this problem. So now the magnetic moment then, M, is just given by 50 amps times 10 square meters, and I'll bring out 10 to the minus 2 in a second here, and then times our unit vector. So our unit vector is 2/7 ax plus 6/7 ay minus 3/7 az, and then this is times 10 to the minus 2 because the area was square centimeters. So I'm bringing the minus 2 out, and then again, so we do that multiplication, and we just have 10/7 in the x direction plus 30/7 in the y direction minus 15/7 in the z direction. Nice. And that is amps times square meters. And that is our answer.